induction. We're going to change colors here. Induction is a really cool principle. In a statement, this is what it is. Relative motion between a magnetic field and a conductor will cause voltage to be induced in that conductor. Relative motion between a magnetic field and a conductor induces, and I'll put brackets, causes voltage on the conductor.
Did you say on, not in?
Yeah, it doesn't matter. I use in for current. Current flow is in a conductor, voltage is induced on a conductor. Voltage we call potential, nothing's happening. It's potential energy. And so you'll see it probably in this book. We induce current, we don't induce current. We induce voltage. You hook that voltage to something, current then happens. So you don't induce current directly, you induce volts. And that is induction in a nutshell. Now you do have to really pay attention to this statement right here, relative motion. I'll show you what that looks like. Let's pretend that this is a conductor and this is a magnet. I can put a magnet here like this, and I can take this conductor, and when I go like this, past that magnet, this conductor will have voltage in it. That's no different in any way, shape, or form than holding the conductor stationary and taking the magnetic field and moving it. The relative motion, you don't care how you get it. There needs to be a speed difference between those two things for voltage to be induced. Any questions about induction? Because that is it. That's 100% it right there. In a nutshell, that's induction. Now, we have a whole bunch of things that take place because of that. That's how transformers work. Transformers themselves work off of an induction principle. So we have what we call mutual induction transformers and auto transformers. So mutual induction is really, oh, that's a transformer inducing voltage on itself versus two windings of wire, that's it. And that's the cool part. Suddenly you're like, oh, well, once you just keep this in mind, anything to do with the magnetic field and the wire, you're gonna have volts somewhere, as long as they're moving. If they're not moving, no voltage is induced. That's slip, we're gonna get to that in a minute. So you're like, oh, okay. You have to have relative motion, have to have it. There's a formula, you guys have probably seen it. It is the most important formula in all of electrical training. It looks like this right here. E equals VLD. Have you guys seen that formula at all yet? Mm-hmm. Yeah. E, induced voltage. That's what it is. E is electromotive force. V, anybody remember what V is? V. What is it? V. Close. We've got three things that we care about here. Yeah, the other ones are easy, right? V is flux. You gotta have a magnet. It's flux density, actually. V is flux density. And I'll just put, that's a magnet. However you get that magnet, I don't care. Whether it's an electromagnet or a permanent magnet, you need a magnet for V. L. Oh, the length of the conductor that's within that magnetic field. So we're gonna have a length there, so L is length. Oops, here, length. And then of course V, what do you think V is?
Velocity.
Velocity, hey, sweet. You guys got this. Velocity. Man, that's awesome. Because with this statement right here, what we just talked about, relative motion induces voltage. How much voltage? Well, as long as you have flux density, well, that's our magnetic field we're talking about, absolutely. As long as you have that, and as long as you have a length of wire, well, that's our conductor we're talking about here. So there's those two parts, and then you have a velocity. Well, that is the relative motion. And so it's like, aha, that actually explains how we get induction to take place. We induce voltage on a conductor. Now here's the cool part. That's what we call a direct proportion formula. Yeah, that's awesome. Okay. Any one of these goes up, I increase any one of those three things. What happens to the induced voltage? It goes up. You're like, well, that's sweet. Spin it faster, move it faster, more volts. Add flux density, more volts. Add length, that's really hard to do in a machine that's already built, right? But add more length, more volts. That's cool. Any one of those goes up. Any one of them, E goes up. And just so you guys are smarter than the average power engineer, that's a voltage rise when you see the letter E. We know it stands for volts, right? But then you've also been seeing V in things, eh? V equals IR, E equals, what's the difference? Very simple. Whenever you see E, that means a rise of voltage. And whenever you see V, it means a drop of voltage. And so Kirchhoff's voltage law, he's one of these old physicists, we don't care a lot about history, but the guy that came up with this has a really, really cool statement. The sum of the rises in a circuit must equal the sum of the drops in a circuit. Your series circuit stuff when you did it, all those resistors have to add up to what you applied to them, right? Well, you applied E, and you had a bunch of V's, and the V has to equal the E. That's literally what it means. So when you see the letter E, that's a generator, or an alternator. You see the letter V, that's a light bulb or a motor. Those are drops, those aren't rises. That's cool. So now when you see that formula, absolutely, interchange E and V all you want, but now you know if you're truly being sort of specific about it, that's what E means. I'm gonna pause. Any questions on that part right there, you guys? Seems pretty straightforward, doesn't it? Because now the rest of it gets pretty easy, honestly. We have to keep this in mind, and we have to keep this in mind for every step of what we talk about with these two machines now. So we're going to start with this guy, the squirrel cage induction motor. Marvel of science. Historically, Nikola Tesla saw this in his head. He literally could see this work in his head. He was working for Thomas Edison at the time. Thomas Edison was Mr. Direct Current. Hated all things that didn't make him lots of money. Tesla threatened his monetary gain by having ideas that weren't Edison's own. This is no bullshit, this is the actual story. So Nikola Tesla drew this in the sand on a beach with a stick to understand it. And he's like, yes, this will work. And he bugged Edison so much that Edison finally told the rest of the engineers and the people that build motors and alternators, like, just build it. God, I need this guy to get off my back. So they did, and it worked. And then all kinds of things got crazy. Nobody knows about Tesla that much unless you research that history, but he is the person that actually gave us the power that you're using today. Without him, we wouldn't have lights in this building. And that's no bullshit, that's the truth. Edison was Mr. DC. You can't go a long ways with DC. At least you couldn't at that time. Which means that the only communities that were anywhere were right beside the hydroelectric facilities. They were right beside the steam plants, because you couldn't go 15 miles and feed a town. But with alternating current, you can. With AC, you can. And that's all because of the magic of that. And the most efficient machine known to mankind, the transformer. We take a transformer and we step voltage up really, really high, so the current's really, really low, and it's the current that equals losses. But we can get a long ways away with really low current, have very minimal losses, and still get a lot of power at the other end. But you can't do that without a transformer. You can't take 500 volts DC and make it 50,000 volts DC, not possible. It is now with our modern electronics, which is really cool, but the cool thing is you can take any AC voltage and make any other AC voltage you wanted easily with a transformer. You ever been told how efficient a transformer is? You talk efficiency, right? You guys know efficiency, boiler efficiency, steam efficiency is huge, it's awesome. That's why we still love steam. We take steam and turn alternators to make power. Transformers, 99.975% efficient. They're so efficient, we don't even give a crap about losses in a transformer when we do calculations. You just go, whatever goes in is what comes out. It's got no moving parts. It makes very little sound. There's a little bit of heat. No windage, no friction, none of that. It's like, man, this thing is awesome. Yeah, more or less 100% efficient. And so therefore, suddenly with AC, we can do cool things. All of this is about AC. And the AC we're talking about, particularly today, is three-phase power. So you guys have seen the waveforms probably already. Line A, line B, line C, red, black, blue, 1, 2, 3, all of that stuff. We're gonna split that apart. We're gonna explain that one piece at a time so we understand what happens in the stator of all the machines. I'm gonna add this word first, stator. Very simply, stationary. That's what it means, stator, stationary. Rotor, rotational piece, right? So it's like, rotor made sense, stator, why stator, stationary? It doesn't move. Now, one of the big hardships for you guys is you did DC machines already. We reverse the roles when you go to an AC machine. So don't think anything to do with DC when you start talking AC, because it's not the same. Even the design of the machine completely changed. So it's like, okay, that's cool. We used to have a stator, and that housed the field, the electromagnetic field of a DC machine. It's not what happens in an AC machine. The stator, in this case, is now what's called the armature. Have you heard armature? Heard that word? Simple definition. An armature is, I'm not even gonna write it down, an armature is where torque is developed in a motor, and it's where voltage is induced in an AC machine, in an alternator. So it's where you get the power from. Whether that power is electric power or mechanical power, the armature is where you get the power out of a machine, which is kind of cool. Obviously, in this machine, when we start talking about where we get the power out of a motor, it's gonna come out of the rotor. But if it's an alternator, it comes out of the stator. So the armature is a really tricky word because it kind of floats around depending on what machine you're looking at any one moment. Don't worry, understanding the principles themselves will lead you to the right answer on armature.
You're saying it's trans.
Pardon me?
You're saying it's trans.
It's trans, yeah, it's a non-binary. I don't know what you call it.
Can you, maybe, just write armature under stator there?
In this case, I'm not going to, because in a motor, the armature is the rotor. In an alternator, the armature is the stator. And so like I said, that armature switches positions whenever you look at a machine. So you just have to remember, if it's a motor, where do I get power from? Horsepower. That's what a motor cares about, horsepower. It's like, okay, that's from the rotor. That's the armature and motor. But when you talk about an alternator, you're turning the rotor with steam. That rotor is inducing voltage on the stator. Where do I get electrical power from? The stator when it's an alternator. So yeah, you have to be really careful with armature, rotor. Motors, rotor. That's where you're getting your power from. Alternators, it's the stator. That's where you're getting your power from. Because in that point, what you care about is electrical power. Okay, three-phase principles. Well, you've seen the waveform. I'm guessing you probably did alternators already. Does that sound right?
Well, we've done the waveform, you got an idea about waveform.
It's really cool. And I can actually demonstrate all this stuff with you guys, and I will, but probably not today because Mike, the other guy, needs the lab all day. I can show you exactly how this works, and physically, but it's best to have the preamble of the theory. Why does it do what it does? Let's take a look at the waveform. I'm going to draw line A first. Here's my sinusoidal waveform, line A. Let's put that's called line A, or line 1, or red, black, blue in our book. Very cool. What we do for a motor is very simple. I'm matching color code. You see how these two poles are red and that sine wave right there is red? I take that voltage supply, and we're only going to look at one of the three phases first. I take that voltage supply, and I wrap it around these poles. And when I say wrap it around, I literally take a piece of wire, and I wrap it around these poles, just like that. And then that piece of wire comes down here, and it carries on, does its thing. And then this end comes out, it ties to the other end, all of them, becomes a wide connected system. Don't worry about that. But here's the cool part. When I do that, and then I apply that voltage to it, at this moment right here and right here, there will be no voltage going through that piece of wire. No voltage at all. But what's really cool is, as that sine wave rises, I'm applying voltage to a piece of wire. At this point, at the peak, that is the highest voltage we can apply to that piece of wire. And here's the part that's really cool. All this magnetism principle, Here's another one of those cool principles. We already talked about induction. Magnetic field goes by a piece of wire, you use voltage on it. But the next cool thing is, take a piece of wire and run current through it. You know what happens? A magnetic field is formed around that piece of wire. It's the opposite of induction. It's actually creating a magnetic field simply by running current through a piece of wire. How do you run current through a piece of wire? Put voltage across it. Voltage across anything that's got resistance has current. How do you make more magnetic field? More current. They are directly proportional. The more current I put through a piece of wire, the bigger the magnetic field is around that piece of wire. That's cool. We're now moving into what's called Lorentz force and Lenz's law, motor action. This is really cool though, because what happens now is when I do this, when I put that voltage across that piece of wire, it creates a magnetic field all around the piece of wire. The whole reason we wrap it on a pole, an iron pole, is because that magnetic field, just like current, takes the path of least resistance. It will all concentrate into that iron and turn it into a magnet. That's what happens. Different word, it's path of least reluctance when we talk magnetism, but don't worry about that. I just turned that into an electromagnet. And I turned it into an electromagnet that only operates when this voltage is above 0. And we'll just go, as it's going positive right here, we'll say that the poles on this thing, this would be a north pole, and this would be a south pole. What's really cool is it gets stronger and stronger and stronger, then it's the strongest at the peak, and then it gets weaker and weaker and weaker, and then it stops, and then something really cool happens. It goes the other way through those windings. And the moment it goes the other way through those windings, this becomes the north pole, and this becomes the south pole. It literally switches the pole polarity, simply from the voltage that I apply to it. No other magic. It's the voltage that changes the poles. We're only going to analyze it on the positive side. It makes more sense to just look at it. There it is, positive side. So we're talking this magnet right here, right now. We're analyzing that spot in the waveform. We got that waveform from a wind turbine, from an alternator, from something that makes electricity. What that means is at that moment, right there, maximum field going from north to south, just like that. I'm gonna put a big arrow. That's the direction it's going from north to south, and it will be the strongest field right there. Or in other words, B right here is the best it can be at that moment right there. Most flux density, most magnetism. Does that make sense? I'm gonna pause there. Because now it gets really easy. That's the red poles. But three-phase power is really cool. It's got another voltage that happens at a different time. That's B phase. So there's phase A. And then sometime after phase A, phase B happens. Here's phase B. Coincidentally, this is really hard to draw a sine wave on a board, just so you know. It's going to look a little bit out of scale. Pretend it's all the exact same wave. Here's B phase. Yep, just like that. There's B phase happening. We know that. There's A, B, then C. Well, if we analyze B phase at its highest point right there, the same thing we just talked about with A phase will happen on B phase. And so I'm going to say, okay, well, this would be a north pole for a moment in time, this would be a south pole for a moment in time. It means there would be maximum flux density going from this north pole to this south pole. There it is. And it has a direction. We'll just put the arrow on there to see. Simple, same as A phase did, right? Well, of course, we do have blue as well. Red, black, blue. C phase. C phase then happens. Here it is. Goes in the gaps. We look at its highest point right there. We take a look at the blue poles. Well, that would mean that this is a north pole at that moment, and this is a south pole at that moment. Here's my magnetic field going from north to south. Now this is where the magic happens. But we do have to remember, when we look at this, looking at those magnetic fields and time, they're not all happening at the same time, are they?
No.
Red first, black second, blue third. So I'm gonna write down there in order. This is number 1 field, this is number 2 field, this is number 3 field, just like that. So it goes from here to here to here. And the cool part is that that negative part, It just switches the polarity, and then this becomes south and this becomes north, and suddenly we've got that field again, but guess what? It's still going 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. It's always going clockwise. That's what the negative gives us on this waveform. Don't worry about that. Clearly, what I have going on is a magnetic field that forms, collapses, and then another one forms and collapses, and then another one forms and collapses. The phenomenon, Lenz's law and Lorentz force, is this: that even though it looks like it's on, off, on, off, on, off, in total, how it reacts is a rotating magnetic field. It actually acts like I'm taking this field and physically turning it. That's how it acts for anything that's within that field. Rotating magnetic field. Here, here, here. That means this magnetic field is rotating in this direction at a specific speed. What do you